They land all over the house. All right, hey. This was hopefully the busiest week we were going to have, where we only had 1 day on sections, and you made it. Which means you earned 3 days for this section. Which is good because everybody said they don't like implicit, and that is next Monday's problem. Let's see, we're going to look at 2.4 on Monday and Tuesday next week also. So we will very much look at implicit in a lot of detail on Monday. In my mind, that really is a second section of material. And I'd rather only focus on the first part of the chain rule for now. And based on all reflections I read, that sounds much better. Going into Wednesday. So we go from section 2.4 to section 3.5, which seems entirely random. And it's because chapter 3 is all applications, and we don't want an entire chapter of applications because students tend to like applications less. Section 3.4 and section 3.5 are both sections on word problems. They use entirely different techniques. And we don't want to confuse the two types of techniques by covering them at the same time. So section 3.5 only uses section 2.4. So that's the one we're going to do now so that you know which technique to use on the test. There's no confusion to use that one technique that we just covered with implicit. And then when we look at 3.4, that'll be a little different. All right. So there is some rhyme and reason to that. But it's also completely unexpected based on what we've been doing. All right, so that is, next week will pretty much be mostly implicit the whole week, plus the word problems that basically just use implicit. All right. The best thing you can do for the rest of this course is really understand section 2.3 and the chain rule in section 2.4. We really want to get to the point where, given f of x, we can find the derivative and not make a mistake. Because guess what you're going to do for the rest of the class? Solve problems where the first step is take the derivative. That is really all of Unit 3 is, here's a function, find its derivative, now use that to answer questions. Which means you have to be able to take the derivative correctly. Otherwise, it breaks everything from then on. All right. We don't force you to simplify, so if you're going to the back of the book and checking, it is not a simplified version. It really is like if they do the product rule, it will look like they use the product rule the way they write their answers. That is perfectly valid going forward. We don't require you to make any simplifications. The problem is when you get to chapter 3, the first step is set the numerator equal to 0, set the denominator equal to 0, and solve. That's a lot easier if you've already factored, canceled, and done other things. So eventually, you do have to simplify. I always suggest practicing now, because in chapter 3, you want to learn the material. And if you're then simplifying for the first time, it's kind of adding 2 tasks instead of 1. So here, you already, on the plus side, you already know you have the right answer based on the back of the book, and then you can always try to simplify a couple steps, see if it checks. On a quiz or anything, I count off on a 5 or 6 point problem, I would count off at most 1 point if you simplify wrong. If you've already given me the correct derivative, everything's labeled correctly, and you have the right answer, and then it's just a mistake after that, that is not worth much credit. Or I don't count off much for that. Okay. All right. So we learned the chain rule. We're exposed to the chain rule by what you're doing. Now we actually want to go through it more. All right. I definitely don't expect y'all to learn everything from the resources. Like I do hope y'all get something in a lecture. I always question that when people stop showing up, but you know. I've also done this long enough not to be offended. All right, so let's look at this example. F of x is equal to 3x to the fourth power, where the 3 is in parentheses. So what does that mean? I want to simplify this.
It's a composition.
Yeah, so if I were to simplify, what would it be? That power, because these are multiplied, the power can be on both of them. If I put a plus sign here, it'd have to expand, right? So because these are multiplied, this is the same as 3 to the 4th times x to the 4th. And because I had a calculator before I came here, that's 81. I don't always know all these numbers off the top of my head. All right, the other one, g of x is 2x plus 1 to the 3rd power. How would this be different? Yeah.
Doesn't the exponent have to apply to both parts?
It does. Almost. Here it applied to both parts perfectly. This is not going to be the same as 2x cubed plus 1 cubed. When I have multiplication, I could do something like that. When I have addition inside, I'm stuck. So if I wanted to simplify this, I have to do this. And then you have to FOIL that out multiple times, which is not really the thing I want you to do all day. So if you multiply all this out, you get 8x cubed plus 12x squared plus 6x plus 1. All right, we'll just take that to 3. Had you done this, you'd only get 8x cubed plus 1, and you wouldn't have any of the cross terms because you didn't FOIL it out. All right, so we have two functions, f and g. I want to basically check the chain rule, see why it makes sense. So, number one, what if I take the derivative of f of x? So I want to take the derivative of 3x to the 4th. Had you never heard of the chain rule, what would you have to do? What did we have before we did last night's stuff? Oh, you did do it last night. You're doing 2.3 last night. You only had the power rule essentially, right? Made addition and all those other ones, but really, you made it look like a power rule, so you can use the power rule. To do that, I'd have to use this form, right? So this would be the same as the derivative of 81 times x to the 4th. So I get 81, and then the derivative of x to the 4th says bring down the 4, and then subtract 1, right? So what do I get? Go. Let me just say. Let me write these down. I get 81 times 4 times x cubed. Anybody know 81 times 4? We're letting you use calculators. Yep. Alright, so I get 324x cubed. That's not the important part of the problem. How else could I have done this?
Use a chain rule. You keep them separately as a composition of functions.
Yeah. What does the chain rule say? I have something all raised to the 4th power, right?
Yeah, the derivative of the outside function times the
Basically, ignore the fact that I have stuff in there and just recognize it as I have something all raised to the 4th. So how do you take the derivative of something to the 4th power?
Bring down the 4.
That's the power rule, right? So I would do the power rule. So just ignore the fact something is in here. That seems too good to be true, right? So I know the derivative of x to the 4th is 4x cubed. which is pretty much what I did. I have a 3 sitting in there. Can I just ignore the 3? Like, that's not, this and this are not the same thing. So that's where the chain rule basically says, do what you really kind of want to do, but then you correct it. I'm looking only at the outside part. What is the derivative of something to the 4th? Do the power rule. So I do the power rule, ignoring everything about the fact I have a 3x in there. The chain rule says you are allowed to do it that way. It won't give you the right answer, but there's a simple way to correct it. So anytime you say then multiply by the derivative of the inside, really you're just doing a correction. I ignored the fact that I had an inside. Now I'm accounting for the fact that there's an inside part. So what would I get here? Yeah, what's the derivative of 3x? These are always trick questions sometimes. 3x is a line to slope through. Do we need power rule or anything? Something like 3x, we know the slope must be 3. So I get what? 12 times 3 cubed x cubed, which is 12 times 27 times x cubed, and has to be the same as 324 times x cubed. As far as I'm concerned, you really could have stopped here. Or, well, sorry. Oh, I should slow that one. I would just stop there, probably. There's no reason to bring the 3 out and all that. If I was going to do all that work, why didn't I just do the power rule start? Where I simplified it. But the reason I did that, you want to make sure these are the same thing. I did one way where I multiplied it all out. I did another one where I do the chain rule. They have to give you the same answer. They're both valid techniques. All right, what about g of x? I have 2 ways to do this. One is g of x looks like this, right? But then, for homework last night, what did I need to do? I guess I could not multiply it out, but if I didn't multiply it out, I'd have to do lots of product rules, and anytime you do a product rule of 3 terms, it's awful. So really, the other option is, instead of writing it in this form, we said g of x, I could think of it as this, or I could write it all out and think of it as this. Either one. So let's do the second one first. 8x cubed plus 2x, 12x squared plus 6x plus 1. So what's the derivative? 8 times, bring the 3 down, subtract 1. 12 times 2, x to the first, plus 6. So we get 24x squared plus 24x plus 6. As far as derivatives go, that's an easy derivative, right? And something like that's the best you hope for. I hope on my 4, let's find the derivative problems. Man, if all 4 are just do the power rule, that'd be great, right? This, in some sense, is like what we hope for. This is the easiest derivative we can really find in this class, in some sense. All I do is constant power rule, constant power rule, constant power rule. It's like that is best case scenario. That's not as easy as I'll ever give you. What's the flaw though? Can I do that directly? Okay. first I have to multiply it all out, and I bypass the fact there's a lot of effort to go from here to here. So, if I were doing this at home, I probably wouldn't do it this way. Now that I have the chain rule. What's the chain rule say? Like, there's a lot of work to go from here to here. And then the derivative is easy. So I do a lot of algebra up front, now my derivative's not bad. This one says, let's do a little bit more calculus. I have something to the 3 power. So something 3 power, bring down to 3, make it a 2. That's way too easy, right? All I did was a power rule, I ignored the fact there's a bunch of stuff in the parentheses. So whatever is in the inside part, the parentheses part, now I need to multiply by its derivative. So I get 3 times 2x plus 1 squared plus the derivative 2x plus 1, 2. So I get 6 times 2x plus 1 squared. Did I ever have to multiply a bunch of things out? I essentially did no algebra, but I had to be a little bit more smart with calculus. I had to use an extra rule. I didn't only use a power rule, I also used a chain rule. Is that the same thing? People are shaking their head yes. Shaking your head yes because you multiplied it out in your head and it clearly matches, or because you just assume I did it right twice. And this would be a bad example if they weren't the same thing. So it's 2x plus 1 times 2x plus 1. So 6 times 4x squared plus 2x plus 1. 6 times this. So I do get 24x squared plus 24x plus 1. Or plus 6. Alright, they do check. They had to check. Assuming I didn't make a mistake, they're always going to be the same thing. Why is that? The chain rule works. Right. The second time I did it, I used the chain rule. I have to get the same answer. I can't get a different answer if these rules are valid. Any questions on that one? Taking derivatives, I would say even doing more than we assign in some sense, practicing taking derivatives is the best skill you can have. Any questions so far? Yes?
How many times can you use the chain rule?
As many times as you need. So, yeah, you could have lots of compositions. So I'll do an example of that. It's a good question. Before I do that, here's a fun one. How should you find that derivative? Last night, what would you have had to have done? Multiply it out 4,000 times? It would be awful. In theory, it could be done, but chain rule, what does it say? Bring down the powers. Subtract 1. And then multiply by the derivative on the inside. Insanely more elegant. It did simplify the problem, right? Before I had my ddx over here, applying to everything. What's the chain rule do? The chain rule says, okay, I took care of all this, and now I only need to worry about this one. Am I done finding the derivative? No, because there's still a DDX symbol. That means I haven't really finished doing all the steps I need, but I have rewritten the problem. Instead of having all of this going on, all this is really just kind of sitting here, right? I've computed it. I'm done with this. The only thing that matters now is finding this. So, what happens? This part just, I'm done. There's no DDX symbol. And then what do I have left? What is that derivative?
100%.
100 plus
2x.
2x. Gonna bring the power down. Am I done?
I would stop.
Yeah. There's no more DDX symbols, so this is the derivative. Should I multiply anything out or simplify? Yeah. Could move this into here. Really, the more standard thing would be to take the 2 out of here. Like, this is, in some sense, already factored, isn't it? Leave it alone. It's good. You have the derivative. Quit working. Yes?
So, how would you solve number 51 on the 2.4 homework?
That is a great question. Alright, y'all want to do 51 or a quotient rule? That one has product rules. And I was about to do one that has a product rule, so we could just do that one. Let's see, how many of y'all are here? Y'all came to class on a Friday afternoon? Yeah, a person gave me a talk from Duke yesterday. He was an American graduate school, and like all the faculty have to go to all these research talks. He decided he's the most boring person ever, or the most hilarious person ever. It was that awkward one where you think you should be laughing because you think he's telling a joke, but they never break face or anything, so you don't know. And then we got to the end of the talk, and he was calling audience members by name when they asked questions, and he had been on our campus for a total of an hour and a half, and like met people while getting a sip of tea. So then I realized one isn't the smartest person in the world, and then finally he made a joke, and you realize, okay, he's also just hilarious. So that was our reward for going to a meeting on Wednesday. How about your reward is I do a homework problem that looks way too long? That sound good? Is this one actually assigned, or is it this one just looking interesting?
It was actually assigned.
I wanted to make sure. There's a lot going on there. What does this mean? So I know what's in the videos, and I know some of this is in the golden videos because we were assigned homework that didn't always match what I was assigned. Nobody heard that. Yeah, you have to dub over. Yeah. What does that vertical line with x equals 0 mean?
Plugging x after you're done taking grade.
Yeah, what's the problem here? I never wrote, so I could say f of x is x times 3x squared plus 1 to the 9th. Right? And then what this problem is actually asking is find the third derivative and plug in the number 0. d cubed dx cubed means find third derivative. The vertical bar x equals 0 says plug in 0. Why do we not write plug in 0? is there anything called f of x here? So if I just give you a list, a function like this part, I could say find f of 0, but that requires knowing this is f of x, right? Or say I don't have a function ever written down. That's the same thing as saying this. I never need to say, hey, let this equal f, so that later I can say plug in 0 by putting a 0 in the parentheses. I could just say, here's an expression with a bunch of x values. I really want to plug in x equals 0. How can I write that? I can't just say this is equal to, so this would be equal to 0 times this, which is 0. Whereas if I write something like this, this is not the same as saying 0 times 1 to the 9. What's the difference in those? If you have a bunch of x's, can you just randomly put in x equals 0? That changed the entire expression, right? Here I have a bunch of x's, but I really want to plug in x equals 0. How can I make this equal sign make sense where I just randomly start plugging in numbers? This says, okay, now plug in x equals 0. Replace all the x's with x equals 0. It's a shorthand for, I never told you what is f, what is f double, triple prime, like all this notation. This, if this were f of x, is equivalent to this statement. But I never have to write the letter f anywhere. I don't have to give the name. It is some expression, eventually plug in x equals 0. Right. So that's a little bit of a tangent, but that's notation we use a lot. The other one we do later. You write something like this. This is a shorthand for f of b minus f of a. Plug in the bottom number, plug in the top number, subtract. Great shorthand. We'll do that in chapter 4 all the time. So, but anytime you see this, it just means we're plugging in a number. Why can't I plug in a number now? Yeah, I just get a number out, right? If I plug in a number, I get the number 0. What's the third derivative? There's nothing there anymore to take the derivative of. How do you solve this problem? I have to find the third derivative, and then I can plug in. Until I know what that is in terms of all the x values, I can't plug in x equals 0. Yes?
So basically, just do the left side of the line first.
Yep. It's an elegant way to say get rid of the ddx stuff, and then the last thing you do is replace that x equals 0 part. Alright, so if I want to find a third derivative, I first need a first derivative. To get, I have a function or expression, I can find the first derivative, I can use that to then find the second derivative. I need to know that before I can find a third derivative. I can't just skip steps. You have to do each one. So what would be the first thing here? What should I do first?
Product rule, split it into
Yes. I have this times this. Is there any way to combine those? If I have something that's essentially factored, right? I have a factor here times a factor here. So I do a product rule first. Alright. When I look at that, first thing I see is a product, so what's the product rule say? Leave the first one, take the derivative of the second, take the derivative of the first one, and leave the second. Right? So with product rule, I rewrote this. Now what? How do I take the derivative of this one?
Use the chain rule.
I have big parentheses, bunch of crap in it, all raised to 9. All I care about is the fact I have something to the ninth power, right? So it looks, if I ignore the fact there are things in here, I would say that looks like a power rule. So I do the power rule. Bring down the 9. Leave all of this alone. Subtract 1 from the power. And now fix it. And then multiply by the derivative of the inside. Alright. So that's the first piece. And now I have this whole piece still hanging out, right? So what do I need there? If I want to keep simplifying as I move to the right, what's the ddx of x? This is the line y equal x, it has slope 1. So ddx of x is 1. And then all that's hanging out. So there's product rule followed by a chain rule in there. How do you know what to do next? That is always the hardest thing. When we take derivatives, this is where you need a lot of practice. It's always knowing what is the next right step. If I look at this now, this looks awful, right? Was it really bad when I did one single step? I had a lot of writing, but was the one step really all that bad? What did I do going from here to here? All I do is a product rule. What does the product rule say? Write this, take the derivative of this. Did I take the derivative? No, I just say ddx of this, that means take the derivative. I didn't actually do the work because if you try to do way too much there, you're almost guaranteed to lose something eventually. It's kind of like if you take the derivative of this piece and kind of leave this piece alone, you forget that, hey, I already did something. It's easy to lose track. So product rule, leave this one alone, take the derivative. Take the derivative of the first one, leave the other one alone. Just write it. You don't actually have to do any of the, I still have ddx symbols, they're just placeholders. It tells me what is the next thing we keep doing. That's how you really want to think of these. I have something that's a product, write the product rule, see what happens. As long as I use this notation correctly, it tells me the next thing to do. Now when I look at this, I have something, I have an inside and outside part. The outside part is something to a power. I can do a power rule. Now I can't just do a power rule because there's things in here, so it's technically a chain rule. Alright, but when I look at this, I think, oh, that's a chain rule problem. Chain rule. The weird thing about the chain rule is usually you're using some other derivative rule with it. Here we're always using the power rule with it. As we get into 2, 5, 2, 6, we'll have other things we do with it. But basically it just says, look at this one part, take care of it. Now multiply by what you ignored. And then over here, I kept simplifying, but this was just derivative 1, so I wrote it. Alright. So now what? Does anything there change? Like all that I've already done, all I have to do is multiply by the derivative of 3x squared plus 1, right? So what is that derivative? 6x. And then plus 3x squared plus 1 to the 9th. So if I wanted to simplify this at all, 6 times 9 is 54. X squared times this plus 3x squared plus 1 to the 9th. Now what? Do I have the first derivative? Once I got rid of all the ddx symbols, that was the first derivative. Then it's a question of how much do I want to simplify? And that is a big question here. If I take the next derivative, I need to take the derivative of this, right? So for a second derivative, this had find all the way to the third derivative. So this is a first derivative. The next one says take the derivative. Write it down. Actually, I want to write on
Well, you we've already found the derivative of the right half, so you only really have to find one thing.
Yeah, there's two ways to go. And it's how comfortable you are with algebra. So, this notation, second derivative of where I started with, that really means find the derivative of the first derivative, right? Second derivative says find the first derivative, then take its derivative. So I could have written it this, well, I couldn't have written it this way. Oh, yeah, I could. So I need to know what is this? This is what we just found, right? So I could say this is the derivative of, what did we just find? 54x squared times 3x squared plus 1 to the 8 plus 3x squared plus 1 to the 9. And I like your observation. I want to start simplifying this. It says take that derivative and this derivative. What's the relevant observation there? I already know this one. I already found that one. What about this part? What do I need first? Yeah. To take that derivative, I have to do a product rule and keep simplifying. Now it breaks it apart into more problems. I keep going from there. That is one direction to go. So I'd have to do a new product rule here and keep carrying this. How many terms does this have? Derivative of this is all of this. So like that keeps getting longer and longer. Annoyingly, eventually you plug in 0, and you plug in 0, you actually get a real easy answer because it's a bunch of ones and powers. The other part I wanted to show, this almost always happens when you do the power rule, or sorry, product rule. When you do the product rule, you kind of still have something you can factor. What's the problem with the product rule? It takes something that is nice and factored and turns it into multiple terms, right? It's not factored anymore. Do I have any factors sitting there? Like, no matter, yeah. Do I have a like factor? I might not finish this whole problem, but it'll show you where you can go to do the next step. Like anything in here, you can always make the problem easier or worse depending on which step you do when. And neither is wrong. You don't have to do it this way, but if you want to condense this for the next step, I would do this first. I have something to the 8th power, something to the 9th power, it's the same thing, right? Both of them have a 3x plus 1 in the base. That is a common factor. What is the common factor? It is 3x squared plus 1 to the 8th power. So if I were to factor that out, what am I left with? It's all of these, right? But I still had that sitting there. So I'd get a 54x squared. So that takes care of this whole first term, right? Then what about over here? What's left?
3x squared.
Yeah. 3x squared plus 1 to the first power. because I took 8 powers away. Does this simplify at all? This would be 54 of these plus 3 more, so I get 57 x squared plus 1. I'm all over the place. That is still the first derivative, right? Before I said, hey, I got the first derivative, let's go somewhere else and find the second derivative. And I could, up there, I could keep working on that. But by the time we get to the third derivative, I'm going to have like 10 terms floating around. It is going to keep expanding. What happens here? This one says I could refactor this a little bit. The product rule broke apart my factors. I could combine them. Instead of having this to the 9th power, it's now to the 8th power. Instead of an x sitting here, I get this thing.
Still doing the same things though, right? You're
So,
doing the product rule. and
Yeah,
then-
so now what would happen on the next step? If I take the second derivative now, so all this was fine, but what could I have done is said, instead of using this one, what is the derivative of this? I can use the factored form. 3x squared plus 1 to the 8 times 57x squared plus 1. What rule do I need for that now? Which one do I start with? Still gonna be a product rule, right? And it's not much different than this. But I don't have this extra term sitting here anymore because I factored it all out. So if I keep going this path, which is perfectly valid, I could even rewrite this for this. Like I already found some of these parts that are going to show up in here. But every time I do this, it's just going to get more and more terms. Because it gets bigger every time. I never condense it back. What I claimed here was since we have to keep going to a third derivative, if I only need a second derivative, who cares? Now that I need a third derivative, I could expand this every time, or I could do a couple lines to factor it. And now it's always going to gain an extra term that then factors back. So it'll always be roughly the same amount of work if I keep doing this. But it's because I'm correcting or making it less effort here. So we took this derivative real fast. It's that, and then product rule says now multiply by the derivative of the first one. And then leave the second one alone. Alright. So I get this times, what's the derivative of this? 114x plus, what do I do here? Has to be a chain rule? So I get this. But it's going to be a similar thing is going to now happen after I take this derivative. I have a bunch of these and a bunch of these. I can refactor that one back out and just get one other thing sitting there. So you do all this, you get the second derivative, and then what do you do? You do it one more time to get the third derivative? And then what's the last step? Plug in x equals 0. And when you do, you get a single number, and you're like, I just wasted 3 pages, and all I did was get one number out. And then you check in the back of the book, and it has a different number, and you're really sad. Or it has the same number, and you're proud, and you're like, I should put this on my refrigerator. I just did 5 pages of math, and I got that one number to check. That's like as exciting as it gets when you do math. Go slowly. Notice I write more every time, but I'm not doing a lot in any step. The only thing that's a little different is instead of plowing straight through, if I know I have to keep doing things, maybe simplifying it before I do the next step. Because otherwise, it'll just keep expanding. Here, this is less expanded and it already looks bad. You keep going this way, it's only going to get bigger and bigger every single time. Eventually, you got to turn your paper and landscape so you have room to write. All right, have a good weekend. Don't even